Good morning, students. Welcome to week 5 of your Teleschool. Today we are still continuing our conversation on electricity and magnetism. So, the last chapter or the last section that we covered, we talked about how electrons and the atom and all those things work together, okay? And then also a little bit about static electricity. Today we're going to talk about circuits. So, an electric current. All right. So, an electric current is the net movement of electric charges in a single direction. So, as this diagram is showing, let me grab out my pen here. We have all of our electric charge coming from in this direction. So, we are going in this direction. All right. From the battery's negative side, okay, to the light bulb, and then the light bulb back to the positive side. Okay? So it is measured in amperes, okay? Amperes or amps. All right? So 1 amp is equal to 6.25 times 10 to the 18 electrons, and that is flowing past every given point at past a given point at every second. So that's a lot of electrons. And they just end up passing through because electrons are so small. Remember, when we're talking about an atom, the two things that contribute to the mass of the atom is going to be the protons and neutrons that are sitting inside the nucleus. And then the electrons are the things floating around outside of the nucleus. All right, so the electron cloud, and those don't contribute anything to the mass, meaning that they're very small. So voltage differences, or volts, okay? The voltage difference is the force which causes electrons to flow or the electric current, all right? So when we have a high voltage, they will all want to go in the direction to the low voltage. And that makes sense because whenever we're inside a highly concentrated area, we want to go from that area to a lower concentrated area. Electric current flows from high voltage to low voltage, and this is similar to water flowing from a high pressure to a low pressure. Or let's just use the example of you are at a mall, okay, and the mall is crowded. There's tons of people there, all right? There's tons of people there. By the way, because of this situation going on with COVID, please don't go into any areas that are high pressure, high number of people, because that is not safe. Remember social distancing. Anyway, so in order for you, and here you are, if you're inside an area with a lot of people, you probably want to go to an area with less people. All right, it's going to be more comfortable. You're going to get more opportunity to stand. You'll have some more room to breathe. So instead of going from an area with a low difference to a high number of people, you are going to want to go from the area of the high number of people to the lower number of people, just because it just makes more sense. That is how energetically you would want to work that way. So equal pressures produces no electric flow. All right. So that means that if you have two things with the equal voltage, since they're already at equilibrium or they already have the same amount, there's going to be no voltage, okay? But if you have different voltages, all right, different numbers of electrons, the high number, okay, they're going to want to go to this area of lower voltage or lower number of electrons, because if you remember correctly as well, electrons are kind of weird in the fact that they don't like to be next to each other. All right? They like to be as far apart as possible. So this wouldn't be energetically favorable, or these electrons wouldn't be happy if they were next to each other. They need to be as far away from each other in order to maintain that happiness, okay? So voltage differences occur with batteries and outlets. So inside of your phone, inside of remotes, like to your television and all those different items, you have batteries. All right, and your car also has a battery too. So when positive and negative ends are connected, it causes a chemical reaction transferring electrons from the negative terminal to the positive terminal. Okay, so on the bottom, okay, you'll see the steel plated covering for the negative. All right, and the inner cell cover, the seal or the nylon so that things don't catch on fire. All right, and then you're going to have those currents travel from this spot to here. Okay, so when you have something connected, let's just say you have a light bulb connected here, okay? If you have a light bulb connected to this battery, all right, you're going to be going from the negative end, okay? And then outward, you'll have it cycling in the direction of the positive end. So electric outlets, okay, the things that you see inside the walls, they provide a continuous flow of electrons that are sent to an outlet through a hard wire, goes through the appliance, and comes back to the outlet on the neutral side. So let's actually take a look at this, okay? So we have a place where it will ground that electricity just in case it gets a buildup of too much and then you could get electrocuted. You have the test and reset buttons. So if you're ever having a power issue with your outlet inside the wall, you can press the reset button in order to get it to probably reset your breaker. Okay. So a circuit, as I talked about just the last slide, okay? A circuit is talking about how an electric current needs a closed path for the electrons to flow. All right? If you have an open circuit, there becomes a break here, and then you won't be able to get that transfer of electrons. And that also makes sense because if you're talking about anything else, if you have a giant hole or a giant place where everything can escape from, you're not going to have that flow going well. So if you're going to attach, here's the thing that I normally think of. Okay, so you have your garden hose, okay, in the summer, and you want to attach it to the sprinkler, okay, however that looks. If that hose is not connected directly, i.e., it has a closed circuit between the water hose and the sprinkler, then you're going to have this explosion of water. That is a very bad hose drawing. But you're going to have that explosion of water, and then nothing is going to come out of the sprinkler attachment. All right? Similarly, we talk about this with light bulbs and other electronic devices. So this is displaying an open circuit where we have the negative side should attach to the bottom of this light bulb, and then the light bulb should have a little spot to attach it back to the positive side of the battery. And because that one is not attached, therefore the electrons are going to travel and they're just kind of going to fly away. Okay? And with the closed circuit, we have that negative end attached to the bottom of that light bulb. The top of the light bulb is then back attached to the positive side. So therefore we have this current cyclic flow of these electrons from the battery to the light bulb, from the light bulb back to the battery. And then a switch can be used to go from an open to a closed circuit. So if you wanted to close off this or open the circuit and not allow light to go through, then you would just press the switch and that would create an open circuit. And then a closed circuit, you'd have to reconnect everything back in, and then you have that light being able to come on again. So we have two different types of circuits. We have a series circuit and we have a parallel circuit. So if a current only has one loop or path it can flow through, it is considered a series circuit. So that means that we have a battery here, all right, that's the negative end. We're flowing through that. All those electrons are going through, all right. Goes from this one to this one, all the way back to this one. All right, so since it is a single attached line going from our battery to these two light bulbs, then we call that a series circuit. Now, if the current has two different directions that it can go in, then it is called a parallel circuit. So I like to think of these whenever we're talking about parallel circuits. Typically, they're drawn in this sort of display. And you might recall something like when you have two lines in math and they're, set up like that. They're not touching, they're not going to cross. They're just called parallel lines. Okay? So we have the battery and we have all those electrons moving from that negative end. All right. And then now it can go two different ways. So one can go this way, one can go this way, and then they all still reconvene back and allow them to go to the positive side of the battery. So moving current will flow through the path of least resistance. And we talked a little bit about resistance last time, and then we'll continue to talk more about it. But the idea is that whatever way is the least difficult to move through is the way that you're going to have that current move in. And that also makes sense because if you have a pathway, okay, so you are standing at a crossroads, okay, so two different roads. One road just leads to just a straight, narrow path to your destination. And then one path, the other path, goes over two mountains, a lake. Let me add the lake. Okay, a lake, another hill, some bears. This is a really bad looking bear. All right. And three more smaller hills and then gets to the destination. Obviously, this is the path with the most resistance. So you're not going to take that path. You're going to take this one because it's going to be easier. And that's the same way that these circuits work. So you don't want to take the more complicated path. You want to take the one that's going to get you to your direction the easiest. So let's talk about how to draw a schematic diagram representing a circuit. All right, so as we were shown before, most of these pathways are going to have your battery. Here's the negative side, here's the positive side, and the light bulb. All right, so they're both going to be connected. There's going to be two wires connecting the battery to the light bulb, right? And remember, when you